We have just learned about Chebyshev inequality. In this video, we learn about Markov inequality. Chebyshev inequality is applicable to any random variable, but we require the knowledge of the mean and variance of your random variable. Markov inequality requires only the mean of your distribution, the center of distribution, but it is only applicable to non-negative random variables. So suppose that you have a non-negative random variable. A non-negative random variable is a random variable which its distribution is non-zero only for positive values. That means that if you plot the PDF, is zero here. So for negative value 0, and you have a PDF somewhere here. So if the center of your distribution is mu x, we could use this Markov inequality, and you only need to know the mean of your random variable. So Markov inequality says that probability that, let's say x is bigger than, so let's say this is alpha, probability that x falls in this area is always smaller than mean of your random variable divided by alpha. Particularly here, if you put alpha equal 1, so this inequality is useless because probability of x being greater than mu x becomes smaller than 1, which we already know. Probability is always smaller than 1. So this inequality is useful if alpha is bigger than 1, and as it grows, the probability of x being away from center or x being greater than alpha reduces inverse proportionally with alpha. Obviously, this inequality is not a tight inequality, but it is what we can know, provided we only know two pieces of information, which is the center of the distribution and the distribution being non-negative. The proof is very easy because mean of x is equal to integral of, because we know it is non-negative, the integral should start from 0 and it's going to be x fx of x, and this is always bigger than integral starting only from alpha, because this integral has two parts. Integral from 0 to alpha, this integral is equal to integral from 0 to alpha of the same expression plus integral from alpha to plus infinity. So this part is non-negative. So if I eliminate it, I see that this should be smaller than or equal this value. So if this guy has two terms, so if I eliminate this part, because this is positive, this remaining part becomes smaller. So this integral is smaller than this one. Obviously, this x, because here x is bigger than alpha. So if I substitute x by alpha, the integral will become will be reduced. So I will have integral from alpha to plus infinity. I replace this x by alpha, which is smaller. So the total integral becomes smaller than alpha x f x of x dx. And now this alpha comes out of the integral, so I will get this integral. And this guy is basically probability of x being greater than alpha. And from here, you could conclude this inequality, because you could divide both sides by alpha, and then you can get that inequality. So this inequality is, as a summary, is applicable if x is non-negative and if mu x is known. For Chebyshev inequality, it is applicable to all distribution, but we could use it if we have both mean and variance. Similar to Chebyshev inequality, I could generalize Chebyshev very easily and prove these ones. So for any arbitrary A and beta and n, for all A, beta and n, any integer or non-integer bigger than or positive, you could prove that. So in this inequality, I need these moments, and it is applicable for any A. So for any real number, this real number could be mean or not. But the question is that when which one of these inequalities are the tightest? It depends on your distribution.